Yeah, so thanks for the introduction. So I'll talk about some aspects of the quantum transport and non-equilibrium dynamics in quantum systems. So in general, I'm interested in this kind of quantum system, which can be described by few energy levels, and system is coupled with, can be coupled with two bars or multiple bars, and system is under a non-equilibrium condition. So there is a constant current flow or energy or spin density flow through the system. So I'm interested in this kind of system. So some of the questions and challenges in this direction, what is this out of equilibrium quantum system? The system is open, so it can exchange energy, particles, all these things, heat, all these things with the surrounding environments. System can in general have many body interactions, and system is subjected to non-equilibrium condition. So some of the fundamental questions like the dynamics or transient behavior before reaching the non-equilibrium steady state. Then one can also study the relaxation dynamics towards the steady state. So can we control the relaxation dynamics? Can we slow it down or speed it up? And once the system reaches the steady state, we can study the transport properties in presence of these bars. And one important thing, if we have this open system with many body interaction and non-equilibrium conditions, so often it's very challenging to study these things both analytically and numerically. So what kind of analytical or numerical methods one could apply to study these things? So this is one of the another fundamental questions. Now, these are the small systems. So average behavior sometimes contain limited information. So we also need to study the role of fluctuations for the system. So this is also important. So not only the fundamental perspective, there are practical perspective also, like how do we engineer the different kind of devices like rectifiers, thermoelectric devices, spin polarizers, spin polarizer using the steady state properties of these systems, and how do we can maximize the efficiency of this kind of non-equilibrium devices. So the main challenge is dealing all these things together: openness of the system, many body interactions, and non-equilibrium condition, all these things together. So this is the main challenge. Now, why it's need to study this kind of quantum dynamics or quantum transport? So the demand of increasing devices per device performance leads to the miniaturization of devices. So from 1950s to nowadays, the size of the system is decreasing day by day from centimeter scale to nanometer scale. So in this length scale, we need to study, to make a device, we need to study the dynamics or steady state or transport of low dimensional systems or mesoscopic system or quantum systems. And in these systems, doing experiments are challenging because systems are hard to isolate. We need to incorporate the effects of environments or fluctuation, all these things. And to understand the experimental results, we need to include the quantum effects such as coherence, interference, and other environmental effects. So now how this kind of studying this quantum transport and dynamics play a role in quantum technology? By saying this quantum technology, one could think it's like processing, transmitting, or storing of information. But one of the most fundamental things one need to know for build this quantum technology is the propagation of information. So this is needs to understand this. One needs quantum dynamics. Like dynamics, if we part of a system, the information, correlation, all these things propagate. So studying this quantum dynamics, we can study like thermalization, localization, non-equilibrium dynamics. And once the information spreading, so we can quantify this using this entanglement, this quantity, or the scrambling of information, this kind of quantities. So to build quantum technology, we need this quantum dynamics, quantum information, all these things. And also with information propagation, so the conserved quantities also propagate when we part of a system. So particle energy and spin, all these things propagate. So we can study this kind of transport of this particle energy or spin. We can classify what kind of transport properties like ballistic, diffusive, or anomalous. So I'll tell these things in details. So to build quantum technologies, the main three things is the propagation of quantum information. So that is related with dynamics. And also entanglement and transport are connected, and how the entanglement and transport things are connected. So this is one important questions in these directions. Are they connected, or are they following the same underlying dynamics of the system or not? And the real quantum technologies are open quantum systems. So like we need to know the transport of particle energy, spin, or information in the to the system in presence of these baths. So my broad goal is like understanding how quantum information or conserved quantities propagate, which is fundamental to controlling the quantum systems. So some of the experimental platforms in this direction is just ultra cold atoms in optical lattices. In these platforms, people can actually engineer lattices like 1D, 2D lattices like honeycomb like lattices, triangular lattices, and one can actually incorporate disorder, interaction, all these things in a like controllable way. One can also take the like non-interacting limits also. And one can study like transport properties and the non-equilibrium dynamics in these setups. Another setup is the mesoscopic or solid state systems. In this setup, people actually can design like quantum wires, quantum dots, all these things, and can attach leads to the system and can study transport kind of phenomena. Yeah, so other platforms are like trapped ions and superconducting circuits, these things. But for my work, so this ultra cold atoms, optical lattice, and mesoscopic or solid state system, these two are like two important experimental platforms to see my theoretical results. So I have worked mostly on the classification in the like domain of quantum transport. I have worked on the classification of quantum transport. So why this classification of quantum transport is important? One is the fundamental thing, is understanding the microscopic physical mechanism of the transport. Why this, like for ballistic transport, the particle or everything is propagating without any scattering, it can propagate freely. So this is ballistic transport. For diffusive transport, the particle moves with some randomness, scattering, all these things. Now, if particle doesn't able to move, so this is like localized thing. And it can happen some anomalous things also happening, like which is in between like ballistic or diffusive. That is known as the super diffusive transport, and it could happen the slow transport but faster than localized, which is between like diffusive and localized. So this is known as like subdiffusive transport. So this identification of this transport process of the particles is one of the main motivation to study the classification of quantum transport. And once we study this kind of current, conductivity, this kind of macroscopic transport properties, we can say, so what is the microscopic property of the system from which we can getting this kind of macroscopic transport behavior? Yeah, this is one of the things. The next practical thing is like designing quantum materials and devices. This is determined by the transport properties. Like for spintronic devices, we need to know the spin transport and its control. For nanoelectronic devices, we need to know the charge transport and its control. For thermoelectric materials, we need to give the bias of both like chemical potential bias and temperature bias, and then we should study different kind of conductivity, and we can study the figure of merit kind of thing. So yeah, and we can try to enhance that. So, and we can also it's important to study the transport for the low power electronic devices. And even for the quantum devices such as superconducting circuits and quantum processes, it needs to like study the transport and dissipation and the localization. Another is the experimental relevance. So in modern experiments, like I have in the previous slide, I have also mentioned like ultra cold atoms, trapped ions, all these things, one can measure transport quantity. So once we get some experimental result from this different platforms, can we interpret that from a theory? So this is one of the reason. And also like reducing errors in quantum computing. So to like for like quantum processors, it need like to maintain the coherence, but the scattering impurities, sorry. Yeah. So, but the loss of coherence can be happening due to scattering, impurities, and dissipation, all these things. So, studying transport helps to minimize such sources of decoherence. So the various ways to classify transport properties, one could be the isolated system approach. So in this approach, one could study the time dynamics or like Kubo linear response type of theory. So for the isolated system approach using time dynamics, we can classify transports. Here we don't consider any external path. The transport is from the system's intrinsic dynamics. So in this case, we prepare a system, isolated system initially in localized or homogeneous state, then do the unitary dynamics. The initial state it evolved with the Hamiltonian, and then look at the long time spreading of this mean square displacement of the wave function, or we can see the current correlation also. Now, if the mean square displacement, this follows a power law kind of behavior with time, t to the power alpha.
Sorry, so you were studying these things because like other moments are not computable, or this gives you everything. So these are like, I say, it's like 2-point correlation, right?
So this is for the like single particle thing, non-interacting thing. So non-interacting thing, this 2-point correlation function, you can compute everything. So using like Weeks theorem, like higher order correlation, you can break down into like 2-point correlation. So
this H is so sorry.
This is current correlation.
This is a single system.
Huh?
But single or is interacting?
This is I am telling for the single particle thing. So you can think you can initial state, you can think the single particle is localized at some like central system, and you can write corresponding wave function and then do the unitary evolution of the wave function. And from the psi t, you can calculate this mean square displacement, this kind of quantity. And also you can calculate current correlation. But if you have interacting system, you need to do the density correlation kind of thing, and then you have to look at the propagation of that and that scaling. So that will give the transport classification. But for the single particle thing, so with this alpha, you can. And the one reason is that this x square, this mean square displacement, this is related with the
Someone are willing to say your mic is on mute.
and this is also related to Einstein's diffusion equation. So this alpha equal to 1, this gives like diffusive transport. So this is known from the classical point of view also. And if alpha equal to 2, so this is the ballistic transport, this fastest propagation of these particles. And then if alpha equal to 1, this is diffusive. This is known from the classical transport also. Now, in between the ballistic and diffusive, if alpha is between 1 and 2, this is known as super diffusive transport. And if alpha is between 0 to 1, so this is subdiffusive, and alpha is 0, so it's t to the power 0. So it's particles not spreading at all. So this is localized or no spreading. But in this classification, we don't have any external bar. This is totally from the isolated system dynamics.
You mentioned that it's a closed ion.
Yes, I think.
And it's a single particle.
Yes.
So where it is diffusing into?
So yeah, so you can think that like single particle, the initial state is the single particle localized at some central site, and then you look at the wave function spreading. So wave function will spread as the time propagates. So if it's localized, it will not spread; it will remain like that. If it if the propagation is ballistic, it will like this moment and this x square average mean square displacement. This will give like t square kind of scaling. So yeah, this is one way to classify.
I forgot the definition of current. Is it delta? How the current is defined? It's like the derivative of wave function?
No, current you in this system, like you can like d any dt, like if average total number of particle ddt of that, you can get current. Oh, here the current you can more microscopically you can write JT, like this is like a commutation of H with the current operator. So average of yeah.
But it's not a charge system or something. It has to be like symbolic. This is not current in like what kind of current?
Current is like the flow of probability, right? That's something. if I remember.
From in terms of wave functions, also here you can write, because there is another definition will come in the open system approach. So yeah, here it's more like current is coming as particle is coming from this in terms of here it's mostly.
So what is the current operator? Or should I think about it? I don't remember. I'm sorry. Should probably know this. But
Yeah, so you have underlying Hamiltonian. So this current operator is like Ci dagger Ci plus 1 for a nearest neighbor hopping model, like minus. So imaginary part of Ci dagger Ci plus 1, something like that.
There is only one seed I can see, right? It's a single.
But you are Hamiltonian have all these things. The initial state is like that, but the Hamiltonian you have.
So it's a multi-party system. Only you start with single excited.
Right.
I say.
oh,
The initial state is like that. Initial, but the Hamiltonian have all these things like yeah.
so Hamilton can create particles.
Yeah. The Hamiltonian is like nearest neighbor hopping type binding model. So it has an on-site potential and this you allowed the particle to hop to nearest neighbor side. So this is the Hamiltonian, and it could have different variations. So it can have disorder, all these things. And in that case, you can also define current operator using the Hamiltonian. And the initial state is only like single particle localized right there. And yeah, so this is the thing. So this is from the time dynamics. We can classify the transport properties. Then the another thing is this linear response theory, Kubo. In this case, Kubo formula. So in this case, also system is isolated, and system is in, let's say, initial state is in equilibrium thermal state like this, and H naught is the like Hamiltonian without any perturbation. Then we can apply a weak electric field like this. And using the linear response theory or like first order perturbation theory, here we can write a relation between current density and electric field, and it is like that in the frequency space. And sigma omega is here the conductivity in the frequency space. And this conductivity is one can show like after the derivation, this conductivity is actually related to this current correlation, like equilibrium current correlation. It doesn't need any bath, but you are calculating conductivity, but it's related to the equilibrium current correlation, so it doesn't need any bath kind of thing. And in the low frequency regime, so we can write how the real this conductivity in general is complex, but in real part of conductivity is related to like this. One can simplify this formula. And the first term is known as the Drudoid, which comes with a delta singularity. And there is another part is the regular part of conductivity. Now, using these two things, one can again classify transport.
So this is this formula is like how general? This is like true for all Hamiltonians?
Yeah.
The Kubo formula is exact equality for any Hamiltonian.
So with the sorry, stupid questions. We have a weak electric field. You said so. We are looking at fermionics here.
Yeah.
And when you say the conductivity is complex, how should I think about it? Because I'm thinking of it in basic terms, right? Like inverse of resistance kind of thing.
But how did
So
yes, because electrical can interact with any charge particle, right?
Sorry, charge particle. I think of the simplest charge particle.
This real part of conductivity, this is related with the mostly conductance, and probably the imaginary part have some different meaning. It could have some susceptibility. I forgot, but now once we have this Kubo formula, we can using this Drudoid, this term and this term, we can again classify transport. So
it is surprising that you have exact equality for conductance for every Hamiltonian. There is a linear response.
But like calculating these things like current correlation or this regular part omega for interacting system, it is numerically challenging. So maybe the formula is valid, but it's challenging for single.
No, I mean to say that it's a linear response theory after all, right?
Yeah, it's a linear response theory, the weak electric field. So
any exact expression is a very strong statement.
Yeah,
because linear response theory will be valid in like certain regimes where the coupling is weak, like you are saying with electric field.
Yeah, but here you don't have any bath. So it's still like isolated. Everything is from the isolated system. So the open system thing will come later. So.
And also, I'm guessing it says for low frequencies. I'm guessing it must be correct.
Yeah, it's omega tends to 0.
Yeah, that is what I think that because
It's an approximation of this. For low frequencies, I think it's a good approximation.
it's a linear response theory, right? So you are time dependent for doing time dependent
perturbation and taking only the linear term, also the other terms.
Okay, you can go.
Now, if this transport classification, if the D equal to this druidoid is like non-zero, so then it's ballistic. This is known as druidoid. It comes from the Drude theory in the.
Or Drude?
Drude weight, yes, kind of weight.
Drude.
Yeah.
So
Now-
it's constant, is it? Is D or-
D is a constant thing, and with that we have this delta singularity.
It's a
And
delta function.
yeah, and this is a regular part. Now this D is finite, then the conductivity is diverging with this delta singularity. So this is like ballistic transport. Now, if this D equal to 0, then everything is have to be to classify transport or conductivity. So everything has to be come from this regular part of the conductivity. So in omega tends to 0 regime, is this sigma regular part is gives some finite value. So that means the system has some well-defined conductivity. So this is the diffusive transport. Now, if D equal to 0 and in the omega tends to 0 regime, the sigma regular part have some different dependence of omega. Let's say it has omega to the power minus gamma with gamma greater than 0, then it's again diverging, and this is known as super diffusive transport, which is between diffusive and ballistic. Now, if it follows like omega to the power gamma with gamma greater than 0, so then it's like 0 conductivity. So this is insulating behavior. So this is known as subdiffusive transport, and it can happen. It's exactly 0. It doesn't follow any power law like thing. So this is the localized thing. So in this theory also, we don't have any external bath, and it's only valid for the linear response.
So,
Now it's has to calculate D.
Yes. And it's very easy. I'll show later how to.
So it's not dependent on the experimental design where I do that experiment to find what D will correspond to.
That you can do, or from microscopic Hamiltonian, you can directly calculate to do it.
So if I just want to dump it down, so you have say a coupling between electric fields say by alpha, then you are computing coefficient of alpha in the expressions. You're computing expectation value to the order alpha.
Yes. Linear.
So this means there will be corrections. With
There is some more other term. So if the
yeah, so that is what I meant actually. Yeah. So this is the linear term. There will be higher order corrections in the coupling parameter.
Yeah.
Hmm.
Now we have this classification of transport from this isolated two ways from the isolated systems. Now we can do the classification of transport properties like open system approach. So here the system is coupled with bath, let's say left and right reservoir. It can have like different it can have chemical potential bias, or it can have temperature bias, or it can have both. And the resulting current is the injection rate of particle minus the extraction rate of the particle. And at non-equilibrium steady state, so always there's a current, and you can calculate conductance is like current by the if we have only like chemical potential bias, then the conductance is the current by this delta mu. And for 1D, for a fixed cross-sectional area, conductivity is like conductance multiplied by the system size, and we consider the cross-sectional area is fixed. So this is the definition of conductance or conductivity. Now for the diffusive transport, this conductance scales as 1 by n. N is the system length. In that case, this conductivity doesn't depend on the system size. That means you have a finite, well-defined conductivity. So this is like the normal diffusive ohmic behavior. Now for ballistic transport, this conductance scales as n to the power 0, so it doesn't scale with system size, but the conductivity is diverging with n, so it's diverging conductivity, fast transport. So this is known as the ballistic transport.
So sorry, in this case, because you are talking about chemical potential only, so this is not an energy conserving system, because you are not talking about temperatures. I mean, temperatures are not equal here, so energy is not
Yeah.
changed.
For temperature, so first I am talking about it could have both bias. It could have only temperature bias, only chemical potential bias, or both.
So
But here we consider it's only chemical potential bias.
So this means that the number of particles are conserved.
Yes.
Okay.
Yeah, and for the ballistic transport, this conductivity is diverging with system size. For the superdiffusive transport, so this is the anomalous transport, like n to the conductance follows as n to the power minus delta, and delta is between 0 to 1. In that case, this conductivity scales as n to the power 1 minus delta. It's also like diverging conductivity. And for the subdiffusive transport, it's n to the power minus delta, where delta is greater than 1. So in that case, conductivity is 0 for the n tends to infinity limit. So this insulating behavior, this subdiffusive transport. And the no transport or localized is like exponentially decaying transport with system size, where this J is the localization length. And here, so if like system size is greater than the localization length, then the conductivity is like 0. So it's also insulating behavior. But now when we study the transport of the low dimensional system in presence of disorder, all these things, so transport often show like departure from this kind of normal ohmic diffusive behavior, and shows like all these anomalous behaviors. And formalisms?
So the current J is itself like injection rate minus extraction rate. So basically the particle
Incoming and outgoing.
But your the average number of particles remains same because like any
dN dt, yeah, equal to 0. It is in the non-equilibrium steady state, one of the steady state approaches. But there's always a current flow. So that is the signature of non-equilibrium.
But previously you said like J is also defined like with respect to like change of number of particles. But here it's like the difference between incoming and outgoing.
Yeah, in that way also, it's many ways to do that. So,
and these statements, so what is the control parameter here?
So yeah, so we have a quantum system. So it has like a hopping. We can use various models like disordered models. Yeah, we can include scattering kind of things. Also the system bus coupling. These things are.
I mean these 5 regimes.
Yeah.
How do I get them?
So we can. So quantum system can have disorder. It can have long range hopping. You can use different models depending on the
Yeah, so for example, I want to see ohmic behavior. Then what are the conditions?
So with disorder, there are some models, 1D system with quasi-periodic kind of disorder. In that case, also tuning the disorder strength one could get. And also, this is a coherent transport, like phase coherence of the incoming electrons is maintaining. With that, you can actually include like incoherent effects using some Boutiquer probe approach kind of thing. So once you like incorporate the incoherent effects, the transport will become diffusive. So diffusive is the natural one.
So I thought there was like some, like you take say low temperature, you get this, high temperature, you get this. Like some analog of that, because we don't talk about temperature here. I mean, if you
no, even at 0 temperature, you can with chemical potential things.
Sure, because it is insensitive to temperature.
Yeah. Yeah, I will talk how we can get this subdiffusive and superdiffusive transport. What kind of systems we have studied, so that is.
And is there something good or bad that if I want to like have something for me?
So the ballistic transport is desirable because it's the fastest, like it's spreading particles, all these things very fast.
Why is it good? I mean, what is good for us?
like in the quantum, information propagation, this kind of thing. If you want to like transfer information or energy, all these things very fastly, then you will desire ballistic transport. Or sometimes you can think like you want to, the localization is sometimes important. Like so I don't know much about that, but in the superconductor.
Yeah, I think very simple. I mean, I'm trying to understand that. So here the conductivity is.
So for the diffusive case, so this conductivity is finite, well defined. That means we can say this copper, this has a well defined conductivity. So this is the normal one. This is we know from the classical physics also, but from the quantum things, we are like getting this low dimensional systems showing different kind of behavior of the transport. Like, yeah.
Yes, in ballistic case,
Ballistic transport, there's no scattering. So particles moving like straight from like this left bar to right bar. It's not feeling any kind of scattering on all these things. But diffusive means it's some kind of randomness or scattering. It's doing some random work and reach to the.
So I want high conductivity basically, right?
Yeah, high conductivity, yes. High conductivity,
So
this ballistic
is the only
where ballistic, yeah, is the most highest here.
Why is that the highest?
Yeah, so it's diverging as n. So on all these things are like diverging less than n.
No, I know, but couldn't it go as n square? Like what prevents what is n square? How do I see that?
Oh, so now, so like all the previous examples are like that, but we find a reason that it is possible to like getting higher than n behavior. Also, we call it like super ballistic scaling of conductance kind of thing. So that
It's possible.
So that's happening.
it's possible, but in the long system size limit, it is not possible. It's like finite size effect.
There is an upper bound somewhere that one can derive,
Yeah.
but this is something that's observed phenomenal.
So these one, I think this kind of yeah. So for infinite size, the faster than the ballistic transport is not possible.
So asymptotically, it's not possible ever. Asymptotically, it's not possible, but say for n equal to n naught, you get n square.
Yeah, so then we get under some condition like yeah, like with instant effects and yeah, there are some special cases where we can get more than ballistic, like super ballistic, but that is limited to finite size, and the infinite size limit is not possible.
Is there an easy way to see why that is that you can't do better than in the infinite size?
Yes, and for superconductivity, like you should get high conductance. I don't know.
That is different. So that for that you need like superconductor thing. So here we are.
So there it will be scaling more than.
No, I think for that case also it's not more than.
So this is
ballistic
scaling. Then ballistic scaling is.
No, I just wanted to see that.
No, they are free things like scattering free transports. No, then it's ballistic. So
when you say that scattering free transport, or so in one of your slides you were talking about, it has transport has application in network, right? In the previous slides you were talking about something. I'm trying to understand how is it
networks. No, networks.
The quantum technology you have mentioned.
No,
quantum networks.
No, networks these don't have application. I am saying that yeah. So the fundamental question for all these things is the propagation of particles information.
Yeah. So when you propagate the particle.
Oh, networks. Okay.
So in that case, how does it happen? So when you send a particle to a fiber, so is that question is relevant in your context? That I wanted to understand.
So we study mainly this models and lattice systems. Model different kind of lattices and study transport through these systems. Yeah, fiber.
So I didn't understand what do you mean that what does it affect?
That instead of lattice, the edges that you have, think of these edges as optical fibers. But then the propagation angle will also depend on the fiber. Right? So something here.
Mostly these are like fermionic transport.
Yeah.
And optical fiber, this may be bosons. So yeah, so and to study this, we can use different formalism, the non-equilibrium Green's functions, master equations, scattering methods. I have mainly used non-equilibrium Green's function technique. So in that case, for master equations technique, we have to consider the weak system bus coupling. But any non-equilibrium in the non-equilibrium Green's function method, so we can consider like arbitrary system bus coupling. So if the system is non-interacting, if it doesn't have any many-body interaction, in that case, NEGF is exact to study all these things. And it is also known as like Lambda or Boutica type transport formalism. Now the question is that, so like So there are different kind of transport classification which will we use. So does all the approach classified transport provide same result? So depending on the complexity of the problems or experimental setups, we should use different kind of approaches, and the different approaches may not give same classification of transport, especially for the anomalous transport like subdiffusive or super diffusive cases. The main difference between this isolated and open system, one is for open system we have bath, and for isolated system we do not have bath. But without this also, there's the main difference is the taking of limit of time and the system size. For the open system approach, we take the long time behavior. We reach steady state fast. That means we take t tends to infinite limits fast, and then we are looking at the system size scaling. But for the isolated system, we consider the system is infinite, and then we are looking the time dynamics. So, and these two take limits may not commute for different models. So, and that's why the different approach may give different results. And for the open system approach with systems microscopic details, we have additional parameters such as chemical potential, temperature difference, system bath coupling. This can we can control this and get different transport phases also. And for open system approach, we can study beyond linear response also. We can increase the voltage bias as much as we want. So what is not possible in the scope of country, that is also limited to linear response theory. So there is various aspects of studying the quantum transport using isolated and open system approach. So what we have one can study this equilibrium persistent current. What is that? Let's say you have a metallic loop kind of geometry, you apply a flux to the system, and at zero temperature, if you take the ground state energy derivative with the magnetic flux, so this is known as persistent current. So once this current established, this doesn't decay other than if we have some decoherence parameter, then it can decay, but without decoherence, it's as known as persistent current. And taking the another derivative of the ground state energy with the magnetic flux, here you can calculate Drude, what we got in the Kubo conductivity. So this is the quantification of Drude, and more, this is ballistic transport here. So Drude gives non-zero Drude gives ballistic transport, and more persistent current and Drude means more transport. So one can study the interplay of disorder, long-range hopping interactions, and various loop geometries, and study the ballistic transport in this way. Another thing we study localization properties and transport using isolated systems Kubo formula approach. And here we find an interesting result that if we have a long range hopping and quasi-periodic disorder together, then the localized state is as if these states are not exponentially localized states. These are power law localized states, and the power law localized states also can give diverging conductivity. So we find super diffusive transport behavior of this power law localized states, which gives diverging conductivity.
So are these your papers?
Yeah, these are my papers.
So, and the persistent current that you defined?
No, persistent current we have not defined. Persistent current is known, but we studied different systems in presence of, long range hopping and all these things. So yeah, persistent current is known from, and in this paper we have studied first time that if we have this quasi-periodic kind of disorder, it's one kind of disorder where it's not completely random disorder or not periodic, it's in between. So this quasi-periodic and this long range hopping, if the system cannot hop only nearest neighbor, it can hop in all the possible way. These two things together can give rise to super diffusive transport even for the localized states. And then can we use this kind of transport properties for efficient quantum devices? So we then connected this kind of ladder system with quasi-periodic potential and see the current behavior, and we got rectification effect. And we have shown this quasi-periodicness and give high rectification of current. Now I'll talk in details the microscopic understanding of the out of equilibrium anomalous subdiffusive transport phases in clean system. These are our papers. So so these two papers I'll talk in detail. So now why subdiffusive scaling of conductance could be important? So it's a slow transport, but it's exponentially larger than the localized. So it's though it's like zero in the n tends to infinity limit, this conductance zero, but for finite size system, the subdiffusive conductance is still important.
So subdiffusive was the 1 over n to the 1 minus alpha. Or which one was subdiffusive?
That is like 1 by n. It is lower than 1 by n, like slower than 1 by n, but larger than the exponentially decaying with system size. So it's like 1 by n to the power delta. Delta is greater than 1. So this is subdiffusive. Yeah, so and this is not a normal diffusive behavior. So we need different microscopic theory to understand this transport mechanism. And disorder and disorder and interaction together can lead to this kind of subdiffusive slow transport phase. And thus, the most of the previous studies are the numerical observation, and the analytically is not understood well why this subdiffusive transport is arising. And such transport phases often show some criticality, like localization, delocalization, transition can show like subdiffusive transport behavior. So in our works, we give a microscopic analytical understanding of subdiffusive transport phases in a clean open system. So the story started with studying the persistent current and Drew rate in a clean long-range hopping system. So why long-range hopping system is interesting? So it allows like distant sites to communicate directly, and so it follows a power law decay, this hopping, and this kind of power law decay 1 by m for alpha. Let's say m is the number of neighbors, and with this alpha we can control from the long range to short range regime. So it has this controllability, and interplay of disorder, long range hopping, all these things can give rise to interesting transport properties. And this long range hopping is also experimentally relevant for different platforms. So what we did, we studied for this model, this long range hopping model, fermionic model. We study the persistent current. So we can write the dispersion relation analytically for the system, as we don't have any disorder, it's a clean system. And then taking the ground state energy derivative, we can find persistent current, and taking another derivative of the ground state, we can get the Drew rate. And we find that k tends to zero limit, this dispersion relation is non-analytic, and the group velocity is actually diverging between when this alpha is between 1 and 2.
Can you say a bit more about the Hamiltonian? Does it have a name, first of all?
It's a Hamiltonian with long-range hopping model, Hamiltonian. So yeah.
So this has like interesting phases there.
Yeah, so so this phase is appearing because we want to study persistent current Drew rate. So we have applied a flux to the center of the ring. So and because of the flux, so there's an Arnold-Bohm effect, and this wave function occurs this kind of phases.
It's not random, is it?
No, it's not random. It's there's no randomness. You applied a flux. So m is the neighbors, number of neighbors. M equal to 1 is the nearest neighbor. M2 is the next nearest neighbor. All these things. And in capital N is the system size, and the phi is the flux. So this phase is a deterministic phase. So it's due to the Arnold-Bohm kind of effect. So if you have a ring kind of geometry, if you apply a flux, so
if m is very large, alpha is greater than 1, right?
Yeah, alpha I consider greater than 1. Yeah.
So when m is very large, then the interaction term is going to 0.
This
strength of the long.
Farther you go, less interaction you have.
Yeah.
You want it to decay.
Yeah.
Yes.
Otherwise, it's
very non-local.
And when so at m equal to 0, m equal to 1.
M equal to starting from 1. Yeah. M equal to 1 is the particle from this to this.
So you said that it translates between two type of things. So one is long range, one is short range, right? So m can.
So tuning this alpha parameter, you can do that. So
zero.
Alpha is greater this alpha infinity limit. So that means all the other only the nearest neighbor will survive. So
due to the
Oh, alpha infinity by m equal to 1 is only thing that matters.
Right.
Okay.
So yeah, tuning this. So for different models, it shows different kind of transitions from long range behavior to short range behavior. So in this study, so we studied the drudoid, this measure of conductivity as a function of filling fraction. So we can fill particles in this system. So it seems that for alpha, when alpha is between 1 and 2 in this regime, when we have a very sub-extensive number of particles, the drudoid is diverging. And
these all computations in ground state of this Hamiltonian or
this is like at zero temperature, yeah, ground state, taking the derivative of the ground state energy. And ground state also you can calculate analytically. So this is
yeah. So ground state you can compute, and these are all properties of the ground state.
yeah.
And one small question, could you explain a bit more what you meant by the unknown form effect? I'm not very familiar with this. I remember the unknown form is, like you take it around, it still retains the phase, right? It doesn't.
Yeah. So wave function is occurring this phase like it will get an additional phase e to the power I5 because
that is never in the Hamiltonian.
But yeah.
Property of the phase. How do you connect it to the Hamiltonian? Can you say?
Yeah, this hopping will be modified by that. The phase.
Go from one to the other. You're saying I'll pick some fraction over phase,
Yes.
so that's why I'm adding.
Yeah, this hopping amplitude is wave function will pick, and that this this hopping is related with the wave function. It's hopping of the electrons.
This phi is like, is it the electric diagonal form effect or there were two, right?
This is the magnetic field.
The magnetic. The phi. Which one was the vector potential at the depth?
Phi with different.
Yeah,
here it is.
Forgotten is the y axis and the electron. So
P plus the momentum will modify by this flux.
And this ground state computer, this this energy computer, this is standard or you did it?
No, it is a standard.
Yeah.
But for this model, we have to find this divergence of this drudoid for the small filling fraction. This is our work.
So that is just for illustration, these graphs. Like you have analytic solution for
Yeah,
just to show us what they look.
Not all of them for this Hamiltonian.
Yeah, for this is a clean Hamiltonian.
Of course.
Yeah, this is a clean system. So yeah, we have.
Yeah, right.
So here we can see that for alpha between 1 and 2 for small gamma region, the drudoid, that means the conductivity. So this is a very high conductivity. And if when alpha is greater than 2, in that case, it seems like gamma is high. So we did this kind of plot, like for which filling fraction this drudoid is maximum. So it shows a transition that alpha equal to 2. In this region between alpha equal to 1 and 2, sub-extensive number of particles are giving high drudoid, whereas for alpha greater than 2, it seems like that for when the particle this filling fraction is high. So it shows some kind of transition from long range to short range transition. So
and transition you must be checking with some divergence or some derivative or something, right? Because this might you must be checking this phase transition in some sense.
So this is
or just a normal transition.
Yeah, normal transition kind of thing. Yeah. So this alpha equal to 2, this phase transition, this is depends on the model and which observable we are looking at. In some models, alpha equal to 2 may show this long range to short range transition behavior, and there could be some other models where this alpha equal to 2 may not matter. That will show it in that case.
Because the graph, it looks like it's a bit more than 2.
Yeah, that is the rule. That depends on the system size also. As I go like more large system size, only numerically finite size effect, it will show like exact 2. So here we find more current and conductivity due to less number of particles. Then we ask the question, what could be the effect of such non-analyticity of k tends to 0 in open system transport properties? So then we attach this kind of clean long-range hopping model with two bars and look at the like conductance scaling. So we can we have a clean long-range hopping. We have the lower bandage. We have the upper bandage. Now, if we fix the chemical potential of the bars less than the lower bandage and upper bandage, we find this kind of scaling like n to the power minus 2 alpha, which is subdiffusive transport behavior. And within the bands, like mu, when mu is between these two things, then this is a ballistic transport behavior. And if we fix the chemical potential at the bar exactly at the bandage frequency, we get this 1 by n square kind of subdiffusive behavior. So if you do a phase diagram plot as in parameter space like mu and alpha, we get a two ballistic to subdiffusive transport phase transition. Like outside the bands, its conductance scales as n to the power minus 2 alpha, and within the bands is ballistic, and at the bandages it's like 1 by n square behavior, which is also subdiffusive, but the scaling is different. And the critical point of the phase transition are the band edges. And in this paper, we provided a microscopic and analytical understanding of these subdiffusive transport phases outside the band edges. And this can be explained by the non-analyticity of the dispersion relation at k tends to 0. But it is notable that at the band edges, it shows 1 by n square behavior, which doesn't depend on alpha. So this is true for even for the nearest neighbor model also, because it's alpha independent. So, and this, it needs different microscopic understanding. So now, yeah, now I'll talk how we are getting this 1 by n square behavior at the band edges. So that's why we now couple a nearest neighbor hopping model with the like two bars at different chemical potential. And
I got lost. So,
Yeah.
how did you define a band edge?
Yeah. Okay, band edge, yeah. So you have a dispersion relation. So the minimum energy and maximum energy. So d, k, d, yeah. So k equal to 0 and plus minus pi will give the dk 0. So in that case, you can get the minimum or maximum energy. So these are the band edges. So k equal to 0 will give the minimum energy, so lower band edge, and k equal to plus minus pi is the higher energy. So it's like a band edge.
And then in the next slide, what was the diagrams of that?
Yeah, so this is like, one is the alpha is this long range hopping exponent, how the power law is decaying, and mu is the chemical potential, this Barth's chemical potential.
So you have mu1 and mu n in the diagram.
Yeah, we have mu1 and mu n, but we are studying actually conductance, that means linear response. We can write mu1 equal to mu and mu n equal to mu plus delta mu. And delta mu tends to 0. We are tends to 0 in the linear response in presence of Barths, and mu we are changing mu and the alpha.
So the number of particles I'm thinking are already in both the initial and in
Barth, yes. And yeah, it's particle hopping from here, it's injecting here and extracting. And yeah, in this plane, if we just change the chemical potential, we will get this kind of phase transition.
Is there such a thing as mu2 in the diagram above, or mu2, does it exist somewhere in the diagram, or it's just labeling mu1 and mu capital? And I'm just trying to understand why it's called mu1 and mu capital.
Oh no, it's coupled fast side and nth side that way.
So
let's say it's an n-side system, so it's
Yes. Sorry. Sorry for all this.
No.
Trying to understand.
Yeah.
Right.
And
And
this is
could
the
you
ball.
explain those diagrams above those?
Yeah, so let's say we have this mu1 equal to mu and mu n equal to mu plus delta mu, and we said delta mu is very small. Now let's say this is the system band, like this. Let's say this is the system band. System is this, like this is the system. System has the energy. You have all the energy levels of the system. So
Is it the spectrum?
this is the system's energy levels, and the chemical potential of the bars I can tune from like here to here. So let's say we put chemical potential of the this left reservoir here, and it's slightly different here. Then you will see this phase. Let's say we keep both the things like near the band edge, so we get 1 by n square behavior, and within this energy spectrum of the system, we'll get this ballistic behavior. And if both outside, we get again n to the power minus 2 alpha. And yeah, this is the lower bandage, this is the upper bandage of the systems. Yeah. So then tuning this.
So y-axis is the energy, the internal thing is the spectrum of the system, and the
Yeah,
left and right is
right. This is the tuning controlling parameter of the bath. Yeah, this is, and at the bandages, this is 1 by n square. This is alpha independent. So this doesn't depend on the long range hopping. It's true for the nearest neighbor also. That's why now we have to understand the microscopic reason why this 1 by n square behavior is coming. So that's why we consider this kind of nearest neighbor hopping models.
So, and how does it depend on phi? Because phi should also appear somewhere. Phi
No, there is no phi. It's an open system. So previously it's an isolated system. We have this.
What's a different slide?
Yeah, it's a different slide. So this here in this way you can study the isolated system things. So it's have a ring, isolated ring. You apply flux and taking the ground state, and now it's an open system thing. So now you are attaching bath. You have opened the system. It's now there's no phi.
So what is the Hamiltonian? Because I thought that was
the Hamiltonian. Yeah, Hamiltonian will be exactly like this, but you don't have this phase.
That's what I was saying.
Yeah, so 1 by m to the power alpha this, so you don't have this phase.
Okay, that's a
Yeah, yeah. Yeah, so to understand this, we consider a nearest neighbor hopping model. So now this is the Hamiltonian. So this is the on-site term, and this is the hopping term. It's can hop only to neighbor, nearest neighbor site. And here we can consider periodic on-site potential. So we consider this so that we can get different bands and multiple band edges. So if Q is the periodicity of the on-site potential, then we get 2Q number of band edges. So we can check our theory like 1 by n square kind of scaling in different band edges. So that's why I consider a nearest neighbor hopping model with periodic on-site potential with periodicity Q.
Yeah, understand. When you have so many bandages, I thought bandages was just like the spectrum. And
Yeah, so now if you have like Q periodic, you have two periodic potential, let's say two things like epsilon A is one at site A you have epsilon A on-site potential energy and site B epsilon B, and then it's repeating. Now you'll get two bands with a band gap tuning this strength of the potential energy. You will get two bands, so you will have 4 band edges. And if you have if you like make the periodicity more and more, you will get more bands and more band edges.
So when we say band edges, it's kind of like a rough term, right? Because you can actually look at the entire spectrum.
Yeah.
Right?
Yeah. So we want to see this kind of subdiffusive scaling. That's right.
Okay.
Yeah. Now we have this this Hamiltonian. Now we can write the discrete Schrodinger equation for this lattices like this. Yeah. So like how this H psi equal to omega psi, we can write in this way. This psi I, this the wave functions at different sites, and how the wave functions at different sites are connected is given by the transform matrix. And for the nearest neighbor model, it's a 2 by 2 non-Hermitian. It's always a non-Hermitian matrix. But for the nearest neighbor model, transform matrix is a 2 by 2 matrix. Now, as we have a Q periodicity, we can write down the transform matrix of the unit cell. And it has this form. Now, the system band structure is connected with the transform matrix in this way. If we take like trace of this TQ, equal to 2 cos k, this gives the system's dispersion relation. And we can also write the eigenvalues of this non-Hermitian transform matrix. So this is a transform matrix with determinant like 1. So in terms of trace of this transform matrix, we can write down the eigenvalues. Now, when this band structure connection is satisfied, then the eigenvalues of the transform matrix are complex. Now, at the band edges, when k equal to 0 or plus minus pi, so minimum or maximum energy, this term is equal to 1. That means the eigenvalues of the non-Hermitian transform matrix coalesces. So that is the like exceptional point or non-diagonality of the transform matrix. So we found that the band edge is the like exceptional point of the transform matrix. And when this equation doesn't satisfy, that means the this greater than 1. So this gives the real eigenvalues. So tuning some parameter of the parameter, we get all the eigenvalues of this non-Hermitian transform matrix. You can get complex eigenvalues, real eigenvalues, or this exceptional point of kind of behavior. So now at the band edges, so we get this exceptional point degeneracy of the transform matrix.
So could you explain what an exceptional point was? I was trying to find your slide and got distracted.
Oh, so so these are the eigenvalues of this 2 by 2 transform matrix. Okay, so in terms of trace of this, you can write so determinant 1. So
Sure.
Yeah.
Someone followed.
Yeah. So now at the band edges, k equal to either 0 or plus minus pi. So trace of TQ, this is equal to 2. So like the eigenvalues 2 by 2, so this term will vanish. So the two eigenvalues are same, and also the eigenvectors for for the 2 by 2 matrix, if the two eigenvalues are same, then eigenvectors also same. So this is non-diagonalizable. Then so this is known as the non-diagonalizability or the exceptional point degeneracies of a matrix, and here is the transfer matrix.
Is this not Hermitian?
No, this matrix is not Hermitian. It's automatically not Hermitian, so it's connecting.
So exceptional point would be like where it becomes complex, or
No, where the two eigenvalues collapses, and it's no more like a non-diagonalizable, so you cannot diagonalize it. So now we'll see what was the effect of this exceptional point of transform matrix in transport. So, and this will help to explain this 1 by n square behavior at the band edges. So here the connection between transform matrix and two terminal this non-equal steady state conductance. So this conductance is proportional to transmission probability, which is like non-equilibrium Green's functions 1 in its element mod square. And here like Green's function is like inverse of this matrix. Here this is like the system single particle Hamiltonian. These are the self energy terms coming from the left and right bath because the baths are attached to the system. And yeah, taking the inverse of this, one can found this Green's function. And this Green's function mod square can be written in terms of this determinant of this matrix, this matrix in this way. And it's a tridiagonal matrix because we have considered a nearest neighbor hopping model, and this determinant can be calculated using the iterative approach, and it is connected with the transform matrix in this way. It's actually very easy to see. Just if you want to calculate the determinant of this tridiagonal matrix, this will automatically, you will get some equations, and you can write in this matrix forms. Now, at the band edges, the transform matrix cannot be diagonalized. So now to calculate this thing, this TQ, the transform matrix to the power n, what we can do, we can do a similarity transformation and make it into a Jordan normal form, and which will, from there, it's like easy to show that the determinant here appears, it's proportional to n, and thus this conductance scales as 1 by n square. So this transform matrix of a unit cell has exceptional point at every band edges, and we get this universal 1 by n square scaling. And within the band, this has a complex eigenvalues of transform matrix, and this will give like oscillatory behavior of the conductance. This gives like ballistic transport behavior. And outside the band, real eigenvalues of transform matrix. So this is exponentially diverging this determinant to system size, and it will show this localized behavior. So here we have plotted the eigenvalues of the transform matrix. We can see that we have considered a binary lattice. We have like two bands. We have 4 band edges, and if we see the eigenvalues of the transform matrix, we can see that these dotted black lines are the band edges, and at the band edges the eigenvalues are coalesces. And outside the band edges, eigenvalues are real, and within the band edges, it has complex eigenvalues. As in terms of conductance, we will see that it shows like non-analytic change at the band edges. Outside the band edges, it shows like exponentially decaying behavior, and like within the band, it shows like ballistic scaling of conductance, and at the band edges, it shows like 1 by n square kind of subdiffusive behavior. And this non-Hermitian properties of transform matrix can explain this. So we have given a unified way to understand the origin of subdiffusive transport in a clean two-terminal settings. So it's like mobility edge-like phenomena. So in 1D and 2D system with the disorder, random disorder, all the states are localized. But with 3D system with random disorder, one can get a critical energy below that. All the states are localized, and greater than that, all the states are extended. And this critical energy known as like mobility edge energy, and the chemical potential of bath for the nearest neighbor hopping model. It's like a mobility edge like behavior. It distinguishes two kind of transport phases, and it's a new kind of dissipative quantum phase transition because most of the dissipative phase transition people either tune the system bath coupling of the system parameters, but here we are changing some bath parameter and getting this kind of phase transition. Now within this two-terminal setup, if we attach some Bouticard voltage probe kind of thing, which are giving the equivalent effects to the incoming particles, then we can get additional interesting scaling of conductance for finite size, what I have mentioned previously. That is the super ballistic scaling of conductance. And one can explain this from non-Hermitian properties of the transform matrix and the same coherent effects together can give this kind of interesting scaling. Yeah, and the scalings, all these things, what I've talked about at the band is transport. This is robust against weak disorder, low temperature, and little shift from the band edge energy also, and it works for any multi-band systems at any band edges. So we did further extension.
Before we go on, I had to there was another meeting I forgot about, so I got a bit distracted. If you go back further to the back, sorry, in this slide, could you explain again, please, how I should think about the band edges? Because you mentioned that these vertical lines are the
band edges. Yeah, so this here we are changing the chemical potential of the bath.
Yes.
And looking at the eigenvalues of the transform matrix in the first plot. So these are the four Q equal to 2. So we have two bands and 4 band edges.
So which are the 2 bands? The fat one?
Yeah, this region 1 band and this region 1 band. Yes. And these are the outside the band edges. Yes. So here you have real eigenvalues, and within the bands you have complex eigenvalues.
And how did I interpret real and complex eigenvalues?
So so here real eigenvalues, so this dotted line are the imaginary things, and the solid lines are the real part. So it's
what is the physical interpretation of real and complex lambdas? What did they correspond to?
Yeah, so you'll see in the effect in the conductance.
In the conductance.
Yeah. So as you have real eigenvalues outside the band edges, you will see the exponentially decaying conductance. Within the band, you have complex eigenvalues, so you will see ballistic behavior. And at the band edge, you have this exceptional point degeneracy. So here, that's 1 by n square subdiffusive behavior at the band edge. So here we have explicitly show these scalings.
And these things are like you have closed form solutions for these.
Yeah.
Oh wow.
We have this all thing we have been done analytically. So for nearest neighbor. And then we also extended for this not long range. If we finite range hopping model, like nearest neighbor, we have additional next nearest neighbor in this.
This is nearest neighbor, right? For the thing
this is nearest neighbor, yeah. But this non-Hermitian transfer matrix, the dimension will increase. So if you add another neighbor, so then it's the 4 by 4 matrix, and you will have a different interesting spectrum. You have higher order exceptional point degeneracy. Like your 4 by 4 matrix, you can 4 eigenvalues can coalesce. Like you have 6 by 6, so the different variations can happen. All these things we have.
And could you also explain why we wanted to consider 2 bands?
Oh no, we can consider any number of bands.
That is for illustration.
That is for illustration, yeah. So you can do it, and all these bands will show similar effect. And all these band edges, you will get this 1 by n square kind of behavior.
And why is there so much noise thingy in the?
Oh, here.
Yeah, what is this? Because if it's analytical.
This is.
No, in the figure above for G.
Here. Yeah. Oh, this is the oscillation.
This is the oscillation.
Oscillation is So here also analytically you can see oscillatory behavior of delta 1 and you have to take the mod square of this and yeah.
So oscillation you mean in the conductance itself is oscillating as you're changing the
chemical potential.
Oh,
Yeah, but like in this scale, microscopic scale, if you do the system size scale, you will see some kind of oscillation, but it's like n to the power 0. You can scale it will not vary much. It's exponentially decaying, and at the band edges, so 1 by n squared. So, and if you take different examples like Q3, 4, any band edges will show a similar effect.
Thank you. Yes, sorry.
Yeah, sorry. And then we are calling it like a mobility edge like phenomena in a clean system. So mobility edge appears in a system with disorder, like 1D and 2D system with disorder shows no mobility edge, but in 3D system,
What does it mean?
yeah, so mobility is an energy separating like localized states and delocalized states. So there could be some critical energy. Before that, let's say all states are particle states are extended, and after that localized. So all the localized state will show the localized transport, and the extended state will show ballistic transport. So this mostly happened in a disorder system, one gate, and also 1D system with quasi-periodic disorder, one can get this kind of mobility edge kind of behavior. But here we have a clean system, and changing the chemical potential of bath, we can getting this two kind of transport, like exponentially localized and ballistic, and the band edge is like a mobility edge, the critical energy separating to distinct regime of transport. And yeah, also we are calling it a new kind of dissipative quantum phase transition, because in the most of the previous studies, people show this quantum phase transition in presence of dissipation. People change the system by coupling or some system parameter and look at the non-lithium steady state, non-analytic change in the non-lithium steady state. But here we are changing the bath parameter, like chemical potential, and seeing this. And this change is what you can put different kind of Bach spectral function, you can still get this transition, and it doesn't depend on the system Bach coupling also. So this is universal in that sense. And now you have this two terminal setup. With that, if you
so system Bach coupling, that was through mu, right?
No, system Bach coupling is system Bach, yeah. System Bach coupling here.
Where's the Hamiltonian?
Yeah, this is the Hamiltonian when we are attaching the Bachs, and the Green's function have this. The Bach's information is coming through the self energies, and yeah, the self energies,
Hamiltonian.
And the self energies all have this kind of information of the system Bach coupling also.
Hamiltonian doesn't have any mu term. Can you go back?
No. It's a systems isolated system.
So what is the coupled Hamiltonian?
Now the full Hamiltonian will be like system Hamiltonian plus right Bach's Hamiltonian plus this Hamiltonian, and there will be coupling. The coupling is just a hopping, bilinear hopping.
Not here.
Yeah,
You are saying coupling is not here.
Yeah, it's not here, but she's saying you add it.
Yeah, you can add
this plus the Bachs, and then one interaction between the first and the.
Here you can, coupling terms. That is the full Hamiltonian.
So, sir, what were you saying? You're confused.
No, you are asking where is the coupling? Coupling
it's not here.
No, it's it will enter in these things through the self energies of the Bachs.
That should be important. That are you assuming weak coupling? Is it like linear in coupling or?
This is in this NEGF language. So there is no approximation in the Bach coupling. So it is.
Coupling should have sold itself somewhere, right?
Oh, the self energy term I have not written explicitly. Here it will appear.
What you were saying, it's independent of the system Bach coupling or something. So I got a bit confused. I thought here it depends on mu, right?
No. Mu is the chemical potential of the Bachs. Here.
Isn't that how you're coupling with the system?
No. This is mu.
So how do you couple with the
N should be coupled in some way so that name becomes a variable.
Oh, this coupling is like this. It's a hopping.
So A dagger A should be coupled in some way.
No.
That is not depending on mu, yes.
No.
Yeah, mu will be defined.
Mu is the
I thought that was-
reservoir chemical potentials.
You're saying if you change mu,
No, but you are right. Actually, it's to do some mu times a dagger kind of a thing. Huh?
that's what I thought.
No. Mu times, no. Mu is not, mu is the chemical potential of the bath.
No, mu couples with n, right? And n will be like a dagger a for this box system or ai dagger ai. So, what should mu be coupled with? Like
Mu is coming in this you can think of like initial state.
sorry,
Initial state have like thermal state. Here e to the power minus beta 8.
So mu will be like Lagrange multiply corresponding to n, just like beta appears for Hamiltonian.
Or this
So you have n.
grand canonical ensemble. You can think
Yeah, so
this
it's not-
density matrix of this.
Sorry. Right.
I have not thought about these things. They're very heavy, very rusty.
Yeah. So with this two term,
Yeah, we have about like let's say 10 minutes.
Hmm?
We have about 10 minutes.
10. Okay, then I to
Yes, I
go
will not ask too many questions now. I think we use the 10 minutes to
This-
go through this.
for the dynamics part.
Yeah, I mean, you use them whichever way you want to list. Sorry.
Okay.
sorry.
So then what I previously told, like we do further extension, like we consider finite range hopping, so that the transfer matrix has like larger dimension than 2, and we can get different properties. We have shown exceptional hypersurfaces of transfer matrix and arbitrary order transfer matrix exceptional points, and what are the effects of these on transport. All these things we have studied. Now we want to talk about this quantum dynamics part. So this work I will not mention. I'll tell about this work in detail. So I'm going fast now.
Sorry.
Yeah.
It's your fault. You did so many things.
So this is like quantum dynamics and semiclassical approach. So can we explain a quantum dynamics using some hydrodynamics or classical approach? So this is what this work is about. So yeah, why quantum dynamics important? So we can study transport, spreading of entanglement or thermalization, all these things with quantum dynamics. Now, what is hydrodynamics? So we have like microscopic quantum dynamics, which may be very complex because of various degrees of freedom. But hydrodynamics give a collective hydrodynamic behavior, which could be very simple. So at sufficiently long times and large system size, quantum dynamics can be described in a coarse-grained manner by a small number of conserved quantities like particle energy and spin densities without knowing all the microscopic details of the system. And the conserved density follows this kind of continuity equation. So this is nxt is the density and jxt is the corresponding current. And using that continuity equation, one can describe the transport and anomalous scaling, all these things. So this is the normal conventional hydrodynamics. Now, when we have a system with large number of conserved quantities, like this pre-fermionic systems, it's integrable systems where we have a large number of conserved quantity, then you have many equations like this, and from this you cannot extract all these observables, all these things. Then the generalized hydrodynamics comes into the picture. So when you have an extensive number of conserved quantities, then the full dynamics, this kind of continuity equation we write in terms of the quasi-particle distribution. So this is that. And using that, this quasi-particle distribution, we can get the observable, all these things, transport, all these things.
It is a positive part.
Yeah, for
Just ask questions. I said, go on.
so.
It's just not positive. Everything is fine.
As I go in our work, so it will be clear. We consider this setup. So it's a field system with LS sites, finite system. It's coupled with reservoir, which is, let's say, empty reservoir, and it's an infinite size. And within the coupling has some this GC. And all the other hopping is G, and coupling has some defect. We call it defect. So this is the Hamiltonian, full Hamiltonian, like minus LS plus this I and J, this runs from minus LS to infinity. And this H, we can write, it's a non-interactive system, so you can write in this in terms of this 2.2, this creation annihilation operator, and the small h is the single particle Hamiltonian. We have chosen different kind of defect, like one is conformal defect, hopping defect, and density defect. So
why do you say it's non-interactive where HIG is there?
Yeah, it's non-interactive means so we in our condensed matter thing and all these things. Interacting means we have this higher order correlation, like we have 3 terms or 4 terms will appear. So only 2 terms, so everything is.
So nearest neighbor interaction, Hamiltonian is not interaction.
That is non-interactive. This is hopping. That is not
just hopping. That's not very what do you say?
That is not like electron-electron interaction, like those kind of things. Many body interaction we call that is only interaction.
Okay.
And this hopping is like non-interaction, only hopping and on-site potential.
You have to be able to drop 5 at a space.
Makes sense.
Yeah, so we consider various kind of defects. So one is conformal defect, hopping defect, and density defect. And we choose different defects because if we kind of calculate the reflection coefficient through this defect, for conformal defect is k independent and everything is simplified and analytical things can be doable. And for conformal and for hopping and density defect, these reflections looks like this. Now we can study the dynamics of various observable using exact microscopic. For exact microscopic, we do numerics with finite systems. So the bath is also considered finite but larger than system. So this LR is much larger than LS. LS is the system size, LR is the number of sites in the reservoir. And we study the dynamics of the correlation matrix. So this correlation matrix is 2-point correlation matrix, and any observables for the non-interacting system can be calculated using this correlation matrix, because all the higher order correlation using which theorem you can boil down to is in terms of 2-point correlations. And we do the unitary dynamics of this correlation matrix, and we calculate observables like particle density, current, entanglement entropy, and particle number fluctuations. So this particle density and current, these are related to these elements of the correlation matrix, where the entanglement entropy or particle number fluctuations, these are related to the eigenvalues of the correlation matrix. Now this is the numerics, exact numerics approach. This is the exact thing. Now we'll also do the generalized hydrodynamics approach to calculate the dynamics of the observables. So as I mentioned previously, we have the quasi-particle distribution. Now this is for the pre-fermionic system. So we have, this is the quasi-particle distribution, and we have this continuity equation where the sign k is the group velocity of these quasi-particles. Now this the solution of this is known as the Euler equation. The solution of this thing in an infinite line is nothing but the position of these quasi-particles with plus k or minus k momentum gets shifted by t into sin k. Sin k is the group velocity, and t is the multiplied by t is the distance covered by the quasi-particles. So x is just gets boosted by this t sin k. So this is the solution. Now we have finite boundary and the defect in that case, and the initial condition is like that. All the quasi-particle the quasi-particles are filled in the left side and the reservoir is empty. So this is the initial condition. And we can also calculate the phase-phase density at any time. And the quasi-particles, because of the finite boundary and the defect, quasi-particles now can do multiple reflections. So it can go and reflect back from the defect and again hit the finite wall, and again as the dynamics progresses, it can do multiple reflections. So the phase-phase density is the sum of this sum of these multiple reflections. And here using that, we can calculate the phase-phase density at x less than 0 for the system side or on the reservoir side. And these are the plots that is showing the phase-phase density, and that obeys this equation. Now, once we have the evolution of the phase-phase density, we can again calculate the particle density, taking the integration over the k. This gives of the phase-phase. This gives the particle density, and you can calculate the current like d and dt, the change in the total number of particles in the system. and n is the integration of rho x dx. And we can also calculate some kind of thing called like hydrodynamic entropy, where the eigenvalues of this correlation matrix is now replaced by the phase space density. And if we compare the hydrodynamics and the exact numerics, we can see the hydrodynamics, the black lines are here from the hydrodynamics, and these colored things are from the exact numerics. So in a coarse-grained manner, so hydrodynamics can explain all these things. Only the oscillation it doesn't able to capture. And also current from the hydrodynamics also capture very well this exact microscopic. And even the entanglement entropy kind of thing, if we calculate from the hydrodynamics and the exact, it seems that if we calculate from the exact numerics, so for the system part and if we calculate entanglement entropy for the system part and from the bath part, both are showing same dynamics, but from the hydrodynamics, the system part will able to capture exactly the exact microscopic. For the reservoir part, it matches up to some time and then deviates. The hydrodynamics is not able to capture full time dynamics or entanglement entropy. And we also calculate the particle number fluctuation dynamics. It shows the similar behavior like the entanglement entropy dynamics. And we have also seen that the connection between there's a connection between this entanglement entropy and transport current, like ds dt is always proportional to I in I is current and ds dt.
Last 2 minutes.
Okay. So
we can conclude that.
Mhm.
We can conclude probably that there are too many types that.
Yeah. So this is the main thing about from hydrodynamics. We can able to capture this kind of complex dynamics, and this is true for any kind of defect. And this is universal in that sense. It doesn't depend on the defect or defect strength, all these things. And it's analytically retractable, hydrodynamics is. So summary on overall research. So we have started from a microscopic Hamiltonian, and for this entanglement study, we study quantum dynamics. And there's like entanglement dynamics or the transport thing, and we give the general hydrodynamics description of that, which can lead to universal behaviors. And in the other way, starting from the microscopic Hamiltonian, we study the non-equilibrium steady state transport in a two-terminal setup, and we do transport classification and connect it with some non-Hermitian physics of the transport properties. And the future research plan. So I'm interested in any kind of system like time dependent or time independent or time dependent bias, non-interacting and interacting exotic systems, or fermionic or bosonic system. The broad question I want to study like how the flow of charge, heat, and information in presence of dissipation with no isolated system analog and their application, and the effect of inherently non-Hermitian matrices on out of equilibrium properties, and can we describe the out of equilibrium quantum dynamics using semiclassical approach. So these are some specific questions in this direction I want to study further, and I'd like to acknowledge all my collaborators.